We can start now.
Thank you. Welcome everyone to today's seminar. It's a pleasure to introduce David Sobral from Lancaster University in the United Kingdom, where he's an associate professor or a reader as it is called in the UK. David earned his PhD at the University of Edinburgh in 2011 and then spent a few years in the Netherlands, first as a NOVA Fellow, then as an NVO Veni Fellow in Leiden. After that, he spent a couple of years as a starting grant holder at the University of Lisbon before moving to Lancaster in 2016. David conducts a wide range of observations of the extragalactic universe and uses different large telescopes, both on the ground and in space. The research he does advances our understanding of how galaxies like our own formed and evolved from the primitive universe till today. Some of his most famous discoveries include measuring the decline of the cosmic star formation history over the last 11 billion years and discovering the brightest distant galaxies. He also does a wide range of outreach activities, from talks in schools to workshops, online podcasts, and interviews. Thank you so much, David, for accepting our invitation. You may start when you're ready.
Thank you so much, Anna, and everyone, I guess, watching, mostly here, maybe a handful of people on YouTube. And it's really great. It would be even better to be in Brazil and escape the amazing British weather. It's raining, in case you're wondering. But it's great to talk about the efforts to resolve the hosts of early ionized bubbles at quite high redshift, redshift 7. And I'll be mostly focusing on what we can do using data from Hubble, MUSE, and ALMA. And I will also be focusing on galaxies such as this, on CR7, although I won't really be looking at the artistic impression, but at reality. And CR7, as in 2019, this is the reality. And I'll try to explain why this matters, why it's interesting, and the things we can look forward to with JWST. My talk will also be about the Lyman Alpha emission line, and I'll tell you that Lyman Alpha is a resonant line that scatters, and I'll try to be sort of a Lyman Alpha photon, and don't worry if I scatter around the screen as I try to guide you through the presentation. So this is all part of the plan. Now, if we think, and I guess this is mostly to give a general background and motivation of why I do what I do, and I guess the ultimate question that I want to address is understanding our cosmic origins and how galaxies form and evolve. And this requires us to understand how early galaxies formed and evolved, essentially from the first light and the very first stars to the formation of the first galaxies. This requires us to go back in time by something like 13 billion years. But some of my research also concentrates on sort of the peak star formation activity and also the reasons that led to the cosmic shutdown. Now, the other thing that I'll try to address as well, and mostly because the sources I'll talk about are hosts to early ionized bubbles, is what we call the epoch of reionization, essentially the last major phase transition in the universe, when the universe went from being fully neutral to fully ionized. And to give some background, and in case there's people that never look at galaxies, or specifically at high redshift galaxies, or at some of the lines that I'll talk about, I hope that this is sort of a way to understand at least part of it. During most of my talk, I'll be talking about the Lyman Alpha line, and this means that I'll be talking about the ionized gas. And if you want a pretty picture about the things we're looking at, it should be mostly regions around O and B, the most massive stars that will ionize their surroundings, and hydrogen, when it recombines, it will emit, and the strongest line will be Lyman Alpha. I will also be talking a little bit about stellar light, and specifically the stellar light from O and B stars, a little bit about some of that light being absorbed by dust and re-emitted as a black body in the far infrared, and towards the end, I'll also talk and use the C2 line, singly ionized carbon with ALMA, that essentially is telling us about what's happening in the interstellar medium. But if you are a fan of AGN, they will also come about. And for a lot of the things that we do, we don't necessarily discriminate to begin with. And this is why I have the AGN here. And in principle, all sources should have some sort of AGN contribution. And it's just that for most of them that I'll talk about, this AGN contribution is very low, if any. So it means light, as far as we can tell, is dominated by stellar light and the ionized gas. Now, one of the things that you can measure observationally if you want to look at the evolution of the universe, perhaps one of the most fundamental measurements you can do, is the star formation rate density. And a lot of people have done this first and traditionally using UV light that traces directly O and B stars, or the far infrared that looks at the sort of the processed emission from those O and B stars. And even though there's quite a lot of scatter that you can see here from different methods with different biases, some of them being affected by cosmic variance, I think one of the things that I'm kind of more excited about is the fact that over the last few years, we've been able to derive the star formation history of the universe fully done with emission lines, essentially with the same technique. With H alpha, we can do it all the way up to redshift 2.5, but with lines such as O3 and O2, we can actually extend it to really probe this peak of star formation history. And of course, there's a lot of research in terms of trying to understand why the star formation history is declining towards the present, and also why it was rising very, very steeply to begin with. And in my talk, I'll be mostly focusing on redshift 2 and above before we go into the epoch of reionization. If we want to find emission line galaxies, for example, because we want to determine the star formation history of the universe, or perhaps we want to investigate the stellar populations that are leading to the ionized gas, there's lots of techniques you can use. Traditionally, a lot of people would first pre-select galaxies and they would put slits. And I think over the last few years, the field has been revolutionized by the development of integral field units. With MUSE, you no longer need to pre-select things, which really kind of eliminates a lot of the biases and selection effects. But one of my favorite ways to look for distant galaxies and distant emission line galaxies is through narrowband surveys. And this is something that I started doing during my PhD. I've also built or developed a lot of narrowband filters to look for these lines at different redshifts. This is me holding one of them at the INT telescope in La Palma. And one of the things that I've been concentrating on is putting these filters on telescopes with very wide field of views so that you can search really large volumes in a sort of completely blinded way. So we don't pre-select and we just look for sources which have strong emission lines. And I think one of the things that will be coming online very soon is surveys like JPAS that will be able to do this over the entire sky. That will definitely lead to the discovery and study of some of the rarest emission line sources. So I'm really looking forward to that. Now, to give a practical example of how we can do this, and this is for a survey that I led. This is the slicing cosmos with 4,000 Lyman Alpha emitters. Essentially, what we try to do is to look for signatures of these very massive, very short-lived O stars and the most massive B stars that will ionize the gas and then will lead to emission lines. And one of the strongest emission lines is Lyman Alpha. So this study is particularly focused on that. And for this survey, we've actually used up to 16 different narrowband filters to try to find and target Lyman Alpha at various different redshifts. So to give a practical example of exactly how you go on and do this, you essentially image large chunks of the sky with the different filters. And if you're looking at a galaxy that's, for example, redshift 3.6, then the filters will show you UV light that's pretty much the same everywhere. Now, the great thing is if you manage to find a galaxy at exactly the right redshift to get Lyman Alpha in the filter, that image on that specific source will just light up. So you'll know that there's an emission line because it's brighter in this narrowband or medium band filter. And also, you can even use other kind of continuum features like the Lyman break. So you can see here that this source has a Lyman break between these two filters. And obviously, we don't just use the narrowband filters, we use all of them in fields like Cosmos. And obviously, if you move further in redshift, then this source would not be picked up. but we would able to, for example, get a photometric redshift because it would be breaking around here. So if you do this for the 16 different filters on very wide areas, this is what you can do in a field like Cosmos. So the name comes from getting about 4,000 of these Lyman Alpha emitters from a redshift of about 2 to about 6. So essentially at a redshift where reionization is essentially over. And the great thing about a sample like this is that it allows us to study these sources that we call Lyman Alpha emitters because we picked them by the presence of the Lyman Alpha line, and they've all been essentially selected with the same technique. So we can also look to see if there's any strong evolution in these sources. So very briefly, without going into too many details, but I think this is important to give context. What have we learned whenever we study these Lyman Alpha emitters? And if you've never seen a Lyman Alpha emitter, this is obviously an artistic impression. So this is not real, and we'll come back to this. But Lyman Alpha emitters in general are really low mass systems. So something like 10 to the 9 dwarf galaxies, I guess in the local universe, we would call them. They're typically very metal poor, something like 10% or less solar. They're typically dust poor, very little dust attenuation, although there is some, so it's not completely zero. But also it is important to note that especially below a redshift of 3, Lyman Alpha emitters can also be different from these, and some of them can be quite dusty and massive. And actually some sub-millimeter galaxies or dusty star-forming galaxies can actually also be picked up by Lyman Alpha surveys, and we do that, but they are incredibly rare. Now, perhaps one of the important things to put Lyman Alpha emitters into context is to understand that they're very likely experiencing sort of their first burst of star formation. So the typical ages from the youngest stellar population are something like 10 to 20 million years. And this means that at least the dominating light is very compact. So for most of these Lyman Alpha emitters, they're probably dominated by single, they might be giant, but almost single HC regions. And at low redshifts, these sources, their typical sizes of about 1 kiloparsec, would be extremely rare because galaxies are big. But as we move to high redshifts, actually, Lyman Alpha emitters become much more of the norm. So in a way, studying Lyman Alpha emitters at any redshift is a good way to study sort of analogs of the highest redshift galaxies. And the great thing about doing it at slightly lower redshift is that we can get further details. At high redshift is much harder to get. I think, and without going into too many details, I think one of the really exciting things from this paper that Ali Kosovan wrote a few years ago was to look at how these sources cluster on the sky and to actually infer what kind of dark matter halos they reside in. And curiously, the answer is that they don't reside on a typical dark matter halo, but rather it depends on how luminous they are. So in a way, the faintest Lyman Alpha emitters, they actually reside on very low mass dark matter halos. Some of them, they actually may evolve to galaxies like the Milky Way. Some of them even galaxies like the Large Magellanic Cloud. But galaxies that are very bright in Lyman Alpha within our samples are actually consistent with already residing in the dark matter halo as massive as the Milky Way now. And that means they will likely evolve into sort of elliptical galaxies. And the most luminous ones, actually, they're consistent with sort of ending up in protoclusters, or essentially ending up in clusters. And therefore, we're picking protoclusters at high redshift. So the bottom line here is that Lyman Alpha emitters, depending on the luminosity that you can get down to, you're actually looking at progenitors of all kinds of galaxies and structures in the local universe. And they're also really useful for that. Now, overall, I think it's also really important to realize that when we survey for Lyman Alpha in a complete blind way, and we compare it with surveys for the UV, the results are really quite strikingly different. So as a result of the star formation rate density going down, the UV luminosity density is going down quite dramatically from the peak at around redshift 2 towards the epoch of reionization. But surprisingly, when we survey for Lyman Alpha and we look at the Lyman Alpha luminosity density, so essentially all the Lyman Alpha photons in the entire universe, we actually see that there's a slight rise. And if anything, this Lyman Alpha luminosity density stays constant. So with a background of less and less UV luminosity density and less stars being formed, somehow there's still the same amount of Lyman alpha luminosity density. And I think this is really important because it means that sort of the ratio between the production and the escape of Lyman alpha photons and the amount of UV that we see is dramatically changing as we go from the peak of the star formation history all the way into the epoch of reionization. And this is further evidence that even though at the peak of star formation history, Lyman alpha emitters or the Lyman alpha luminosity density is just a few percent of the thing that comes out in the UV, by the time you get to the epoch of cosmic reionization, Lyman alpha emitters should become way, way more common. And from different inferences, you could tell that there should be at least something like 40 to 50% of galaxies at that point. So this means that something is evolving, very likely the typical conditions, the ISM conditions, and also probably to do with the fact that galaxies become more and more compact at high redshift, and therefore they become much more like Lyman alpha emitters. Now, I told you at the beginning that I was going to mention AGN, and this is just a side note, but it is important to realize that when we pick Lyman alpha emitters blindly, we actually also pick a lot of AGN, and we'll pick even more AGN in very wide field surveys. And that is because once you go above the typical Lyman alpha luminosity, and essentially the samples become completely AGN dominated. Every single one, with very rare exceptions, every single one of the brightest Lyman alpha emitters, a redshift 2 to 3, then essentially all these galaxies are AGNs. And I think one of the interpretations, and you can find more details in this great paper by João Calhau that was published last year, is that the reason why AGN can also be Lyman alpha emitters and at quite high luminosities is that for star-forming galaxies, there's sort of a limit to how bright they can be in Lyman alpha before dust starts to kill their luminosities. So galaxies can form more stars, but they don't look brighter in Lyman alpha because at those star formation rates, there's lots of dust. But AGN do not suffer from that. And the reason why they can get brighter is because in those regimes, actually Lyman alpha is tracing the black hole accretion rate. And even though with a lot of scatter, we can see that Lyman alpha for AGN sort of correlates with X-ray luminosity. So that's interesting on itself, but it's not something that I will focus on for the rest of the talk. Now, I think one of the things that we really need to address head-on is the fact that a lot of people run from Lyman alpha because of how complicated it is. The reason why Lyman alpha is complicated is because it's not just a UV photon. So it's a photon that when encounters dust may well just be destroyed. But on top of being a UV photon, it also scatters. It is a resonant photon. This means that whenever a photon encounters neutral hydrogen, it will actually be absorbed and then it will be released, but on another random direction. So while UV photons can actually sort of travel in a direction and they can go through neutral hydrogen without problems, the non-ionizing ones, Lyman alpha photons have really long paths until they can escape, and many of them will get lost because they scatter so many times that the probability of them hitting a dust particle becomes much higher. So even though Lyman alpha photons should be the most numerous ones in the universe, it comes from an extremely simple transition from n equals 2 to n equals 1 in the hydrogen atom. The physics of it makes it really complicated. And observationally, perhaps the big limitation is the fact that you can measure something, for example, a Lyman alpha luminosity or an equivalent width, but you cannot directly interpret what it means, for example, in terms of a star formation rate or the production of Lyman continuum photons, because we would need to know what fraction are we seeing out. And this is a consequence of when these Lyman alpha photons are produced, they will scatter inside, it could be inside the ISM and also around the CGM, and within the epoch of reionization, even in intergalactic medium. So a lot of these photons will scatter many times and get destroyed, and there's only a few of them that may make it to our telescopes. Some of them may make it directly, obviously, but many of them will make it after kind of sort of scattering multiple times. And sometimes they could even be backscattering. So we may be seeing Lyman Alpha from a region that didn't produce it, actually. It produced somewhere else, and it just sort of backscattered into our line of sight. Now, at this point, a lot of people just run away and they say Lyman Alpha is no good. But over the last few years, we didn't do that. And instead, what we tried to do, like other people have done it for sort of deep surveys, what we did was conduct a wide field survey to try to calibrate Lyman Alpha empirically. So we actually built a filter. This is the narrowband 392 to match an age alpha filter that we had already constructed and used to survey for age alpha. And what this allows us to do is to measure what we call the Lyman Alpha escape fraction, essentially the ratio between what you observe in Lyman Alpha and what the galaxy has produced. So if you measure the age alpha line and you also infer some dust properties to correct this age alpha luminosity, you can use sort of case B recombination to actually predict the intrinsic Lyman Alpha luminosity, and then the ratio gives us the escape fraction. And this has been published in the Kalima survey. So sort of two papers focusing on different selections, but also just a few weeks ago, Yard Matei put out the first paper from the follow-up that will really allow us to sort of pin down the physics of the Lyman Alpha escape fraction. Again, without going into too much details, but I think this picture is quite relevant also to interpret the hosts of early ionized bubbles. When you look at the full sample, and you can look at age alpha, so essentially where the Lyman Alpha photons have been produced, it's in red, and where the Lyman Alpha photons are escaping, you clearly see that the scale lengths are very different. So they're produced in compact regions in these sources. This is at redshift 2, but they're escaping a much larger radii. And this is consistent with these photons sort of scattering many times. And even though Lyman Alpha emitters have escape fractions of something like 20 to 30%, the common or the typical star-forming galaxies at redshift 2, the age alpha emitters, actually have really low escape fractions at the order of something like 1.6%. So most Lyman Alpha emitters produced in the typical star-forming galaxies just do not escape at all and very likely just get absorbed by dust. But one of the important sort of stay-at-home messages that perhaps you can take away from this talk is that even though Lyman Alpha is incredibly complicated, and it is, there's also advantages to that complication. And there's dependence with the escape fraction in terms of stellar mass, luminosity, star formation rate, dust, metallicity, you name it. But it's really hard to calibrate on all those physical properties because the scatter is huge. And it turns out that if you look at all those properties and the simplest observables, the easiest way to calibrate and to actually infer a Lyman Alpha escape fraction is to measure the equivalent width of the Lyman Alpha line. And it actually can get as simple as this. Essentially 0.005 times the equivalent width of Lyman Alpha and Armstrong can give you the escape fraction within quite a good accuracy, at least from something like 0 to 160 Armstrong. And this can be seen actually from low redshifts, where people have studied galaxies that sometimes are named green peas or blueberries or other kinds of tiny little fruits with different colors, depending on how SDSS picked them up, all the way up to the peak of star formation history, and with indications that this might work even at redshift 5. So this is really exciting. And the great thing about this, even from just an empirical observational point of view, is that it works. So even if there was no physical insight, I think this relation is really interesting because with a very simple observable, only takes a spectrum or a narrow band and a broadband, you can actually infer the Lyman Alpha escape fraction of a galaxy and therefore use and interpret Lyman Alpha finally. And I think the interesting thing as well is you can look at this relation from a purely analytical way, and it's not surprising that the escape fraction correlates with the equivalent width. The equivalent width is sort of a ratio between Lyman alpha and UV, but it also depends on other physical properties of a galaxy. So AUV just being the dust properties in the ultraviolet, and this factor psi ion that you can see here is essentially the ratio between the ionizing photons and the UV photons, essentially how efficient a galaxy is in producing ionizing photons. So the fact that there is a clear relation between the escape fraction and the equivalent width means actually that the psi ion and AUV need to somehow be correlated, so they cancel out. Otherwise, there would be sort of a big spread in the relation, even if it depended on equivalent width. It also means that the highest Lyman alpha equivalent widths will have the lowest dust and also the highest production of Lyman continuum per UV luminosity. And before really moving into the hosts of the early ionized bubbles, I think it is really worth looking at the physical interpretation of this relation. And you can do it sort of analytically, so you could derive this equation and check what it's telling you, but you can also do it in a very empirical way. And what I've done here, so this is published in the paper that you see above, is I've generated 1 million galaxies without putting any physics. So galaxies that can have all kinds of combinations of dust properties, stellar populations, and anything else. And if that was the case, if there was no connection between the physics within galaxies, they should actually populate the entire grid. So you see all the points here. So the fact that in the real universe, we observe this relation with a given scatter, you can actually then select that and look at what it means physically. And for example, looking at the potential relation between how ionizing a galaxy is, so this is a ratio between Lyman continuum photons or ionizing photons on the UV, and on the x-axis, you have how dusty or how much dust extinction this Lyman alpha emitters are. So the fact that this relation exists means that these properties need to be correlated in a very specific way. It means that galaxies, if they have really low dust extinction, then they need to be incredibly ionizing. And it means that if a galaxy is dusty, it needs to have a low ionization efficiency. Otherwise, this relation would break and you'd find galaxies pretty much everywhere. But I think one of the most interesting things is the fact that you can even interpret it very simply as sort of a sequence, a Lyman alpha emitter sequence, because the youngest galaxies, you expect them to be essentially dust-free and have stellar populations that are incredibly ionizing. So they would be found in this diagram around here. And as they evolve and the stellar populations become more normal, more like the local universe, and they produce dust, they will essentially move along this relation. And this means that we will find them essentially towards the low Lyman alpha escape fraction and low equivalent widths. And I think this is something really cool to explore, something that we can do already at Redshift 2, and then with JWST, this will become even clearer. And to highlight that one of the big applications of this is if you can actually measure the escape fraction of Lyman alpha photons with just an equivalent width, it means that you can sort of step away from needing the UV. And if you measure the Lyman alpha luminosity and an equivalent width, you can measure directly the amount of ionizing photons. And an application is to derive star formation rates, which are quite accurate for Lyman alpha emitters. The other application is cosmic reionization. So I hope I gave you at least some background to Lyman alpha and that you're not too scared to tackle it, and that even though it's complicated, it can also be used, and there's a lot of physics to discover there. So we can now move into the EBook of reionization and actually look at some of the hosts. And for those of you that are not familiar with the EBook of reionization, it's essentially a time during which the universe went from being fully neutral to fully ionized. And essentially what you need, the ingredients, are ionizing photons, essentially photons with energies in excess of 13.6 electron volt. there are still some debates about which sources actually did it, whether it was faint galaxies, bright galaxies, whether the contribution from AGN is significant or not, whether it's the stellar populations that are different in these galaxies. For example, binary star systems, which are longer lived, may contribute more to cosmic ionization. So this is not what I'll be focusing on. And instead, I'll be very pragmatic. And what I'll focus on is using Lyman Alpha lines and the fact that we can see them at the epoch of cosmic ionization to know almost for certain that they reside in ionized bubbles. So I told you already that Lyman Alpha is extremely sensitive to neutral hydrogen. And it means that even if Lyman Alpha escapes a galaxy, if the intergalactic medium that is very close to the galaxy is still neutral, it means those photons will just keep scattering and the surface brightness will be so low that we won't be able to see them. So the fact that we've now found really luminous Lyman Alpha emitters at these epochs, it means that we have also found some early ionized bubbles that allow these photons to essentially, when they leave the galaxy, they will be redshifted through the Hubble flow until they might encounter neutral hydrogen, but by then they're no longer Lyman Alpha photons and they will just go through it like a normal UV photon. So these profiles will, of course, tell us about the interstellar medium, the CGM and the IGM, but that's not so much the point about this now. And I think the important thing is to understand that if we compare low redshift Lyman Alpha emitter, for example, redshift 2.2, when the universe is fully ionized, we can see the full profile. So typically we would see a blue wing that is not cut off. And what we expect the universe to do at high redshift when the universe becomes partially neutral is that this blue component will be cut off. So if there's no bubble at all, this cutoff will even extend all the way to the red part, and we would see no Lyman Alpha emitter at all, even if the galaxy is there. So the other thing that we can do is actually we can measure the size of the bubble by looking at the difference between sort of this red part of the line and where the blue part is cut off. So a galaxy within the epoch of ionization where this separation is really big means it's residing on a really big ionized bubble. If the separation is small, then it has to be very small. But of course, this requires knowing the systemic redshift. So we know where the kind of the redshift of the galaxy is. And at the same time, it also relies on us understanding the complexity of the interstellar medium effects on these galaxies. Now, what I'll be focusing on are these three different galaxies. They're very luminous. So we named them CR7, VR7, and MUSE for different reasons. And they were essentially discovered what I told you in the beginning with these very wide and deep emission line surveys. And even though they're very luminous in Lyman Alpha, they actually sample a range of UV properties. VR7 is the brightest in the UV, CR7 is the brightest in Lyman Alpha, and MUSE is the faintest in the UV. And they also sample sort of a range in colors in the UV. But instead of just looking at specific integrated properties, what we'll be able to look at is the resolved properties of these galaxies. And I brought back a plot I showed you at the very beginning, but now to focus on the spectral energy distribution and on the fact that with these spectacular instruments, such as MUSE, we can actually spatially resolve Lyman Alpha. With HST, we can spatially resolve the stellar components of the most massive stars. With ALMA, we are able to actually spatially resolve C2 and dusts if we detected it. And soon with JWST, we'll be able to also spatially resolve the rest frame optical lines, which is going to be really exciting. So if we look at just the integrated properties of these sources, we actually realize that all of them are undetected in dust continuum. So this means they're incredibly poor in dust, like the lower redshift Lyman Alpha emitters. And CR7 is a square, but it's still undetected. So some of these sources are as metal poor as Wiki 18, for example. But at the same time, at least for CR7 and VR7, we know that they already contain metals. So we actually detect C2, and for VR7, C2 is actually quite bright. And this sort of confirms a relation that Joritz discussed in his first ALMA paper, that if you know the star formation rate of a galaxy, you can sort of predict the probability of detecting it in C2 with ALMA. So the most star-forming galaxies are very easy to detect. Those with low star formation rates essentially typically remain undetected, like MUSE. But more than just the integrated properties, we can resolve these sources. And Hubble is amazing at doing this already. And for CR7 in 2015, we already knew that it decomposed in these 3 different components. For VR7, it looks like there's a big blob. And for MUSE, which is the faintest, it seems like there's a main component, but then something else, which seems to be quite red. So there's a lot of unresolved issues in terms of understanding what goes on in these sources, but there typically are multiple components. And even though some are extended, most are compact, and the individual components are sort of 1 kiloparsec, something like that. So if you then combine the spectroscopic view from the VLT that tackles Lyman Alpha and ALMA that gets you C2, you can actually measure a shift. So typically Lyman Alpha is shifted. It could be because of outflows, but also radiative transfer effects. So remember, Lyman Alpha is quite complex. And without going into too much details, I think the beautiful thing about these data sets is that even though we're looking at something 13 billion light years away at redshift 7, we can already see resolved structures, so perhaps some shells or outflows in C2. And if you then look at these sources with MUSE, so you look at spatially resolved Lyman Alpha emission, you can actually recover something really similar to the analogs at redshift 2. So at redshift 2, we can actually do it with H alpha. Here, we still need to rely on UV and C2. But what we see is that the production is probably quite compact, and then we see a halo that is much more extended. So for VR7, the picture seems to be that we're looking at the late stage of a major merger. There are sort of 2 components that we can see once we look in 3D at different velocity slices. And the Lyman Alpha halo is actually there, and it's fully consistent with the lower redshift Lyman Alpha emitters. So this means that even though there's some potential kinematics, the galaxy seems to be residing in a fully ionized bubble, because we can see the same properties as if it was at lower redshift. And we also see that the Lyman Alpha velocity offset from systemic is low. So this means very likely that the bubble is big enough, but there are some spatial changes. So perhaps it's not really a bubble, but something that is quite asymmetric. But I think what is really clear, really exciting for JWST is that we can already see evidence of really big metallicity gradients within these galaxies. So we see regions where the UV to C2 ratio is very different across the galaxy itself. Could be because of the merger. It could be because there's many more sort of supernova going off in one of the regions. Now, finally, CR7, we've been able to get exactly the same data. So we can also detect this beautiful Lyman Alpha halo extending many kiloparsec. The great thing about it is we can now extract on different locations. So we can actually confirm that all the UV clumps belong to CR7. We're looking at a major merger. And to begin with, we thought it was a triple merger. In the UV, we now see that there's at least an extra component. And actually, with ALMA, we can see that there's more components. And CR7 is very likely sort of a 6-way merger, which is really, really exciting. And I guess you could see this very clearly in this image here, but I'll come back to it. Now, because we're running out of time, one of the final messages that I really wanted to bring, so the sort of take-home message, is that at least in the last sort of 20 years, we were used at very high redshift of just doing blobology. And the best we could do on very sort of high redshift blobs was to put a slit, maybe get a redshift. But slowly over the last 10 years, things have really started to change. And we're now appreciating the complexity that higher resolution observations are revealing. We're now detecting Lyman Alpha halos, even at the epoch of reionization. And it also means that with ALMA, looking at C2, for example, we have an alternative way to look at these galaxies in 3 dimensions. So we can confirm individual clumps, and we can even confirm and find clumps that Hubble doesn't see at all. So within CR7, there's 2 important C2 clumps that are not there at all in the UV. So it means that these galaxies are even more complex than what Hubble was already revealing. And I think the picture is going to be even more interesting, more complex, perhaps more complicated to interpret once James Webb is launched. And the field of view of NIRSPAC is really perfect for these sorts of systems. And we'll be able to essentially target all these components and maybe even investigate some of the weird features like this weak helium-2 line that seems to be found around the clump B. So I think I will leave you with the summary. I hope I've showed you that Lyman Alpha is complicated, but it can be used. And specifically, once we find luminous Lyman Alpha emitters at high redshift, they really are ideal to study as hosts of early ionized bubbles. And I think I've showed you that what very likely makes them special is that they have multiple clumps. Very likely they had multiple stellar populations. So perhaps they were able to carve their own bubble in sort of waves of star formation. And Hubble, MUSE, and HST are really revealing how complex these things are, and very likely that they result from multiple major mergers. But I think overall, this is really just the first glimpse of what JWST will be able to show once it safely launches and it starts observing these sources.
Thank you very much for your talk, David. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them on the YouTube channel. We'll be back next week with a seminar on multiple stellar populations in galactic globular clusters by Sara Saracino from Liverpool. Stay tuned and follow AstroWorks in our social media for this semester's events. Goodbye. And now we go to the breakout rooms.